Welcome back to the discussion on three-dimensional transformations on the course on computer graphics. In the last 2 hours, we have discussed various types of transformations in 3 dimensions, notably rotation, reflection, translation, scale and shear, and then of course, we had moved on towards the projective transformations, that is orthographic and perspective projections. We have taken a few examples of special cases of projections basically with respect to perspective transformations, and we have seen the scenario of the projection plane and the center of projection or the PRP, projection reference point, and we had seen equations which can be written and the corresponding transformation matrix in perspective projection. We have to look for a generalized formulation of the projective transform, specifically with respect to perspective transformations, and which we are going to start today. And if you look at the screen, you have the picture which gives you the very general scenario of perspective transformation or perspective projection specifically, where with respect to the screen you have the x and z coordinates, or the y and z, you can take right handed system. So, if x is the vertical axis and z axis is moving from the origin O towards the right, you see in the picture, and the vertical axis is x, then of course, what you will have is the y axis will basically point towards you. And of course, if you take similarly the y axis to be vertical, then x axis will point towards you. Okay. So, we are basically projecting onto a 2-dimensional plane, which is the screen, and this entire 3-dimensional picture is what you have to view. And the projection plane, PP is the projection plane which is perpendicular to the z axis. The normal to the projection plane is now the z axis itself, and the projection plane is also along the xy plane. And since we are looking into xz plane, both the xy plane and the projection plane will appear as only lines to us. Okay. Now, we have assumed that the projection plane is at a z distance zp with respect to the origin along the z axis, that is the distance from the origin to the point of intersection of projection plane and z axis is zp, so the coordinates is 0, 0, zp as given in the bottom of the picture, and the center of projection or the COP is along a direction vector given by dx, dy, dz respectively. These are the direction cosines of a vector from the point 0, 0, zp towards COP, and the COP is at a distance q. COP is at a distance q from the point 0, 0, zp, that is the intersection of z axis and projection plane. Actually, you can define a point anywhere in space with respect to any other point, provided the direction cosines of the line joining them and the distance is known. So, distance between COP and 0, 0, zp is q, and the direction cosines of the vector pointing towards COP from the 0, 0, zp point is dx, dy, dz as given in the screen. Okay. And the projection has to be taken for a point p x y z on the right hand side of your screen. This is the point in 3D for which the projection has to be taken. So, the projector ray or the projective ray from point P to COP forms a line L, and that line L will intersect the projection plane or the PP plane at a point say P prime given by the coordinates xp, yp and capital ZP. This is ZP is the same as the 0, 0, ZP because the projection plane is at a distance ZP from the origin toward the Z axis. So, the problem lies that given Q, given dx, dy, dz and given zp, we have to obtain the coordinates xp, yp, xy coordinates of the projected point P prime on the projection plane, which is basically a projection of the point xyz coordinate, the projection point P with coordinates xyz. So, what are the input parameters of the algorithm? xyz coordinates of the point P, zp, dx, dy, dz, q. Okay. So, these are all given to you, and the unknown quantity is the xp, yp, which is nothing but the xy coordinates of the projection point P prime. Okay. So, this is the picture which explains the generalized formulation or the problem of generalized formulation of perspective projection, and if you are not used to the equation of a line in parametric form, which is being introduced today for the first time in this course, we will keep on getting this many a times as we keep going along. The parametric equation of the line between COP and P is given as COP plus T times P minus COP. This is a vectored form of this equation, where the parameter of the line T varies in the range only between 0 and 1. That means, if you substitute T is equal to 0, you are basically talking of a point COP, and if you take T is equal to 1, you have reached the point P. So, as you vary T from 0 to 1, you are moving over the line L from COP to the point P. Okay, so, at point P on the line L, your T is equal to 1, and at the COP on the line L, other extreme, the parameter T is equal to 0. Any other point on the line L which lies between COP and the point P, you have the values in the range 0 to 1. Let us look at how you derive the parameter T when the line of intersection, the line L basically intersects the projection plane PP at a point P prime. And if we can somehow get that parameter T, since the coordinates of the point P and COP are known to us, if we substitute the T exactly, you will get the coordinates of point P prime. The only information which is known to us is that the Z coordinates of the point P prime is ZP. Okay. So, look at this slide as we go along. The direction, as I was telling you, the direction vector from the point 0 0 ZP, which is the intersection of projection plane and the Z chord and the Z axis, is 0 0 ZP, and the direction vector from that point 0 0 ZP to center of projection or COP be the direction cosines given as dx, dy, dz, and q be the distance from 0 0 ZP to COP. Okay. So, I can express COP also as a vector addition of 0 0 ZP plus q, which is the distance multiplied by dx, dy, dz. If you have noted down the figure, please, I hope you have copied the figure. I display the figure once again. So, I am expressing COP as a vector which is 0 0 ZP plus the q vector multiplied by the direction cosines dx, dy, dz. Q is a scalar quantity. Okay. So, that is how COP is expressed here. Okay. So, we will keep going back and forth to the figure and coming back here if necessary. So, the coordinates of any point on line L can be given as x prime, y prime, z prime as q dx plus x minus q dx times t, and similarly y prime and similarly z prime. How do you get this? You get this basically because when we go back to the figure, you have seen the expression of the line L, and the COP is now known. We have defined COP as 0 0 ZP vector plus q times dx, dy, dz, and P is known. So, using this information with a little bit of mathematical manipulation here, you can actually find the coordinates of any point on the line L as that's given in the expression here as x prime, y prime, and z prime. And remember, q is known to us, dx, dy, dz is known to us, zp is known, and z is also known, that is x, y, z. The coordinates of the point P is known. The left hand side is all unknown, x prime, y prime, z prime is unknown, t is the unknown parameter. Okay. As you vary t, you know from the two extreme the two values of the t. But we know one more fact which we are going to put now, using the condition that which I said just now, that the value of z prime becomes equal to zp at the intersection of the line L and the projection plane PP. The line L and the intersection of the plane PP basically gives you the projection point P prime, and that has a z coordinate zp. So, that much is known to us. So, we use that constraint and put it on the third equation, where z prime is equal to zp at that point, and that helps us to obtain the value of this. So, basically what you do is you use z prime is equal to zp, substitute it here on the z prime, the third equation, and then you use that to obtain the expression of t, which is given in the bottom left of this screen. So, this is the value of t at which the line L intersects the projection plane. Okay. So, that is the intersection point, the value of t, and use this t value to substitute in the first two expressions of x prime, y prime, and what you get basically is nothing but the coordinates of xp, yp. Okay. Please please work it out yourself, okay, where you can obtain these, first of all, these three equations x prime, y prime, z prime from the previous expressions given in this slide and in the previous slide, and then of course on the third equation put the constraint z prime equal to zp, obtain the value of t as given here, and you now substitute to obtain the value of x prime, y prime as your xp and zp. So, I will substitute that and give you the final result. Please note down yourself, you have to work this mathematics out yourself, x prime, y prime and z prime first the expressions, then the value of t, then you substitute the value of t onto the expressions of x prime, y prime, and you get your x prime, y prime value as given here is in xp and yp. Okay. I will halt for a moment, please you can copy down the values of xp by p, which you will get by substituting from the in the previous slide the value of t onto x prime, y prime. I go back to the previous slide for a second, where I am talking about these two equations x prime and y prime, substitute the value of t as given here on the onto the first two equations, and you get x prime, y prime as your xp and yp, and these are the corresponding expressions. So, these are nothing but the solution for the generalized formulation of the perspective projection. If you see on the right hand side, as we talked earlier, all the parameters and values are known. What are the values known? X, y and z are nothing but the coordinates of the point in 3D. dx, dy and dz are the direction cosines of that vector from 0, 0, zp towards point COP, and of course, you also know ZP, which is the intersection or the distance of the projection plane from the origin, and that is the vertical distance basically ZP. So, and Q is also known because that is the distance of COP from the point 0, 0, ZP. So, all the parameters on the right hand side are known, you can substitute and get the values of XP, YP, and those are nothing but now the values of your coordinates of the 2D projection of the point in 3D. From 3D to 2D, this is the generalized formulation. Okay. We look at some okay. Now, when you go back to the generalized transformation matrix and use the expression as given in the previous slide of XP and YP, you will be able to obtain, you should be able to obtain the expression of the generalized transformation matrix. I give this as an exercise for you, please try it out. All these expressions you have to write out, otherwise you cannot derive it, otherwise you will easily lose the concept and you will fail to understand the concept. So, what you must do is you must write these equations, draw the figures yourself, understand the vector equations, parametric equation of a line is what you have to use, and then you from the expressions which you have got as XP and YP, you have to get the generalized transformation matrix M general as given here. Okay. So, this is the form, you can please note down the values here. So, P prime is M times P, where M is the transformation matrix, generalized formulation of the perspective projection matrix, and if you use this generalized formulation and which will help you to obtain the 2D coordinates from the 3D point. So, projection of a point in 3D onto a 2D plane, a generalized formulation is given here by M general. Okay. I hope you are able to copy the corresponding elements of this matrix, which you should try to derive yourself. Of course, these have all been borrowed from the book by Foley, Van Dam, Feiner and Hughes. Okay. We look at some special cases from the generalized formulation of the perspective projection matrix, where the matrix type can take special forms and shapes depending upon the values of ZP, Q and the direction cosines dx, dy, dz. The first row talks about the case when the ZP is at the origin. So, you have moved the projection plane at the origin, Q is at infinity, the Q is the distance, that means the center of projection now has moved to infinity. If the center of projection moves to infinity, we know that the projective rays from the point towards the center of projection passing through the projection lane will all be parallel, hence the transformation matrix becomes an orthogonal matrix, and hence we have written M orth. That means it is a transformation matrix for orthogonal case, and the direction vector dx, dy, dz will also take the form 0, 0, minus 1. The 0, 0, minus 1 form of dx, dy, dz is also same for the next two rows. It's basically 0, 0, minus 1 type of unit vector, if you see, is nothing but a vector which is looking towards the minus z axis. which is looking towards the minus z axis, okay, and your view is along the positive z axis, and the direction vector from the projection plane or the plane normal towards center of projection is 0 0 minus 1. Okay, so we have understood what is M orthogonal matrix from a generalized formulation. Second, if you take Zp equal to D, that means wherever it was earlier, Q is also equal to D, and the direction cosine 0 0 minus 1, we get a special case of a perspective projection matrix where my COP is at the origin now, and the projection plane is at a distance d from the origin, and the surface normal of the projection plane is pointing towards the minus z axis. You get the special case of simple perspective projection matrix, and these expressions we have already derived earlier in the previous class. A special case of M prime bar or dash is the case when Zp is equal to 0 and Q is at D. That means the projection plane is now at the origin, and the center of projection is also at the origin D, and if that is the case, you get M prime. I expect you to obtain the special cases of these matrices by putting these constraints, and you get them basically by substituting these conditions on the terms, on the elements of this generalized matrix. Okay, substitute them and get the special forms of the matrices type of orthogonal and perspective. Okay, if and the last point to be noted here is, of course, if Q is finite, which is the case of perspective projection matrix. When only Q becomes infinite, we are talking of orthogonal. Otherwise, when Q is finite, we have perspective projection matrix. The rays converge at a point, the rays are not parallel at all. The generalized transformation matrix defines what we call as a one-point perspective projection in the above two cases. Above two cases means the last two cases as given in the three different cases, special cases in the table here. Okay, I hope you still remember the 1 point, 2 point, and 3 point perspective projection systems in perspective projection. Okay. We come out of perspective projection, we have discussed at length today and also in the last class, and move towards the case of parallel projection. Okay. Parallel projection, I must remind here that you must work out all those expressions which are given earlier for the generalized transformation of the matrix. And in the case of parallel projection, we know that the constraint is that the distance from the COP to the projection plane is infinite. Okay, the distance from the center of projection to the projection plane is infinite. Okay, therefore, if this is the case, what happens basically is the projectors or the projective rays all become parallel lines, and hence we need to basically specify a DOP or a direction of projection as given in the slide here. So, since the COP has vanished to infinity, we do not need to specify the coordinates of the center of projection. Instead, the direction of projection is very important. Basically, it is nothing but the direction cosines dx, dy, and dz. A special case of parallel projection, we have seen different types of perspective and parallel projection. We had seen a chart, we will see that soon, is basically the orthographic projection, which is of very important to designers of graphics, and we say here that the direction of projection and the normal to the projection plane are the same in the case of orthographic. That means the direction of projection is normal to the projection plane. If it is not, also it may become parallel, but it may not become orthographic. Okay, let us look at this chart again, which I was talking about. We had shown this in the previous class also. Planar geometric projections are of two types. I repeat again, parallel and perspective. Perspective are of three types: 1 point, 2 point, and 3 point. We had discussed this all in the last class itself, and also the generalized form today. In case of parallel, typically I will say there are two broad classes. One is orthographic, another is oblique projection as given here. One is orthographic projection, another is oblique projection here. And orthographic again could be four types: the top view, front elevation, side elevation view, typically used by most architects and civil engineering drawings and mechanical drawings as well. And of course, also it could be, we can have an axonometric view or an isometric view. We will see an example where we talk of a top plan, front elevation and side elevation together of one type of orthographic projection. We will also see a case of axonometric or isometric type, and we will see the oblique type projection also. Oblique type could be also two or more types, cabinet and cavalier, but again probably we will not discuss in details. the two different types only we will discuss what is oblique type and how it is different from axonometric or isometric type, and that is again how it is different from the front, top or side elevation. So, first we will move towards orthographic projection, talk about top, front and side elevation views, then move to axonometric, isometric, one example each, and at the end we move towards oblique projection. Okay. This is an example of an orthographic projection which shows the three types of views which you can generate for an object, correct. I was talking of a top view, a side view and a front view. So, here you see typically a structure which looks like a house with a tapered roof. It is basically you can visualize that I have as if put a rectangle at the bottom and then of course a tapered prism type of a structure on the top. So, that is a combined structure, and if you look at the structure from the top projection plane, as you have seen that the projected rays or projective rays are all parallel coming out of the object and intersecting the projection planes. The projection planes are all gray in color. There are three projection planes. Okay. There are projection planes for the front view, there are projection planes for the side view, and the projection plane for the top view. Okay. So, top view is the top, side is on the side, and the front is to the left of you. So, there are three planes, and as you can see here, the projectors for the top view, front view and side view respectively, they are all parallel. I mean, if you take a group of rays for the side view only or only for the top view or for the front view, they are parallel to each other and they come out of the object and intersect the plane and they keep moving towards infinity. They are all parallel to each other, they will never intercept, as you can see here that you can get three different types of views depending upon whether you are having a top view or a front view or a side view of the object. This is a visualization which you must be able to see for yourself. If you look from the house from the side, typically you will have a side view as given here on the right hand side in the gray color projection plane of the side view. If you look from the top, you will have the view as given on the top view. Okay, you will have the line in the middle and two on the sides, and similarly from the front plane you typically have the cross sectional view, I should say. Also from the side view or the front view, you typically have a cross sectional view where you have a square and then a triangle on the top of the cross section as you see from the front. From the side, of course, you will have two rectangles side by side adjacent. Okay. So, these are simple examples of orthographic projections of top view, side view and front view. You can in fact given an object which is very regular in terms of a geometrical shape, I am sure almost that you should be able to draw the corresponding side views. This is a fundamental concept which is taught in almost any drawing class in engineering disciplines, and you should be able to generate the top view, side view and the front view for any given figure, either it is circular like a cylinder or a sphere, or it could be a rectangle or a cube or a cone or a pyramid. Regular geometrical shapes if you take, you should be able to draw the corresponding views. I leave it an exercise to take other shapes. Here it is a planar object which you have been taken, but you can take a sphere or a cone or a cylinder and please try to attempt to draw the corresponding three views for orthographic projection. The other type of orthographic projection was basically the isometric view or axonometric view. They are almost similar. As you can see here, the projector rays are parallel all right, but the projection plane is at an incline, in the sense that it is not aligned with any of the x, y or z axis or any of these x, y Cartesian coordinate frames, and the projection plane normal, we assume at least in this case of isometric projection we will define what is this, although I have shown the figure, and the projector rays and the projection normal are parallel. Okay, let us look at the definition of axonometric and isometric views. First, axonometric orthographic projection. Remember, orthographic type of projections had a side view, front view and a top view, and then axonometric. Okay, they use planes of projection that are not normal to a principal axis. That is what I was talking about. Okay, so the normal to the projection plane is not aligned with any of the three principal axes x, y or z. X, y or z axis is not aligned with the direction or the normal of the principal axis, and therefore you can or you should be able to see multiple faces of the object using an axonometric projection. What is the special case of axonometric? In terms of isometric projection, isometric projection is a special type of axonometric one, where the projection plane normal makes equal angles with the principal axis. That means the direction of projection vector is given as 1 1 1, or it could be -1 -1 -1 respectively. It means that the projection plane normal makes equal angle with each of the principal axis. Okay, so if you take the projection plane normal, it seems to be coming out from the origin. It is neither along any one of the three principal axes x, y or z respectively, and it is coming out intersecting the plane and pointing towards you. We will just go back and have a look at this figure. This is what I was talking about, isometric projection here, and the projection plane normal is making equal angles, direction cosine equal angles with respect to all the three principal axes x, y, z. And as you can see now here, with this type of a hollow cube which I am visualizing with isometric projection, you are able to see more than 2 or 3 faces. Typically when you take a top plan or a side view for a cube like this, you will be able to see 1 or 2 faces mostly, but in this case, as you can see, you can almost see about 3 to about 4 faces of the cube. Depending upon if it is solid, you will see only 3, but in this case if it is a hollow, you will be able to visualize that you are actually seeing 4 faces of the cube, 2 from outside and 2 from inside. Okay. So, we talked of this definition of axonometric projection and then isometric projection, and the last word about this is that all 3 axes are equally foreshortened, allowing measurements along the axis to be made with the same scale. Okay. This is a special case for isometric projection, special case of axonometric projection, which is isometric, where we know that the projection plane normal makes equal angles with each of the principal axes, and the first criteria of the definition of axonometric projection also holds good. That means you use planes of projection that are not normal to your principal axis, so you can place it anywhere, but is in axonometric, but the special case of isometric, it must make equal angles. What must make? The projection plane normal must make equal angles with the 3 principal axes x, y, z, and typical example is the directional projection vector, which is nothing but you can say this is also the projection plane normal is given as 1 1 1, and all the 3 axes are the dimensions of the object along all the 3 axes appear to be equal and same for the isometric projection. Oblique projection, this was a different type of orthographic projection. Unlike the orthographic case, orthographic had top, side, plan and axonometric and isometric as well, which is a part of isometric. So, these are the categories of orthographic projection under parallel, and we had seen in the chart earlier that parallel projections could be classified under 2 broad categories again. One was orthographic, other was oblique. So, we have seen the various types of orthographic projection: top, I repeat again, top view, side view and front view, and also axonometric. Those fall under the category of orthographic projections. Okay. And the other type of parallel projection is the oblique projection, which says, as you see on the screen, you see that the projection plane normal and the direction of projection, they differ. This is very unique in the sense that you are going to have almost for the first time a scenario where the projection plane normal and the direction of the projection are not the same. In perspective projection and in orthographic under the category of parallel projection, always we had a scenario where the projection plane normal and the direction of projections, those 2 vectors were the same and they coincided. But is in the oblique projection, we have a funny case where the projector rays, which usually intersect normally with the projection plane in all other type of projection models, does not happen in the case of oblique. So, you can take a plane and instead of projector rays parallel intersecting the projection plane, they intersect at an angle. So, the direction, the plane normal and the direction of the projector rays, they are not parallel anymore in the case of an oblique projection. We will see with an example a few more points. So, plane of projection is normal to a principal axis. So, we come back to the forms of the special type of orthographic projections, such as top, plan, side, etc., or even perspective projection, where the planar projection is now made in such a manner so that it is normal to a principal axis, or the projection plane normal itself is one of the principal axis, and the projectors, but the projectors are not parallel to the they are not normal to the projection plane. Earlier projectors were moving along the direction of the normal to the projection plane, but they are not anymore. So, how do you visualize this figure? Let us look at this figure. Okay. I hope you will be able to understand this figure, where the projection plane is the gray color rectangle, and we are again taking the projection of a cube. It is a hollow cube again. It is easy to visualize if you take a hollow cube, because you can see the inside lines as well. And the projection plane normal is the z axis. The projection plane normal as given the bottom of the screen as the vector here is aligned along with the z axis or parallel to z axis, and the projection plane normal is nothing but now the xy plane, correct. The projection plane normal is hence the xy plane. And but it is interesting to note now here that the projector rays are not parallel to the z axis. They are neither parallel to z axis nor the projection normal. This was not the case of any other type which we had seen in orthographic odd perspective, but in oblique, that is why the term oblique comes, that the projector rays now come and hit the projection plane at an angle. They are inclined, they are not normal. They are not normal, they are not parallel to the projection plane normal, they are not parallel to the z axis, but they hit on the projection plane at an incline, and this is what gives you what is called as an oblique projection. Yes, it could be useful in certain cases, but difficult to typically derive expressions, but you must know the type of oblique projection as given here. Okay. Just to give an idea of the formulation the required for the generalized oblique projection of a point or a line, if you look at this figure, what we are basically trying to do is that we have taken the projection plane to be the xy plane, we have taken the point to be projected on the z axis, a point P given with coordinate 0, 0, 1. So, hence it is at the z axis, on the z axis, and we intend to project this point through a line on the xy plane, which is the projection plane, and the intersection of that line with the projection plane will give you the projection P prime, will give you the projection P prime. In fact, this point will project there, the entire line will project into a line which will join the origin O. I have not marked the origin, but you can visualize the intersection of the three principal axes x, y, z to be at the origin. So, the line joining the origin to the point P prime, which is marked as italicized L, is the projection of the thick line or the 3D line onto the projection plane. Remember, it is an oblique projection, and that line L makes an angle alpha with the x axis. It also makes an angle beta with the line in 3D. So, this is what you have as the oblique projection of a point or a line. Maybe we can write a few equations on this as we had given earlier. So, the projection plane, as I said before, was an xy plane. I hope you have drawn the previous figure. If not, please draw it. I flash it again here. So, x, y, z, then the point 0, 0, 1 projected on the xy plane gives you the projection P prime, and so the projection plane is the xy plane. P prime is the projection of a point P 0, 0, 1 in 3D onto the xy plane. Okay. And L is the projection of the z axis unit vector onto the xy plane. Okay. I must say here that L is the projection of the z axis unit vector, not that projector line which I was talking about. So, I have talked, you can take a z axis unit vector and projection of that onto the xy plane, because you have to send projectors which are all parallel to this thick line joining P to P prime. One such projector ray is given as P to P prime. You can take any other projection point, the projectors will be all parallel to this line and they will hit the xy plane. Okay. So, I must rectify myself and say that the L is the projection of the z axis unit vector onto the xy plane, and alpha is the angle the projection makes with the x axis. That part is okay. So, what is the direction of projection here? When direction of projection varies, both L and alpha will vary. Okay. And what do you mean by this, that the direction of projection will vary? We will just go back and see. Direction of projection is nothing but the thick line joining P to P prime. So, if you change this line P to P prime, what will happen is basically you are basically changing the direction of projection. Direction of projection is the vector from P towards P prime. So, if we change that, of course, L and the corresponding inclination angle alpha both will change. So, that is what is talked about here. So, when direction of projection varies, both L and alpha will vary, and the coordinates of the P prime, the projection point of P on the xy plane or the projection plane, can be written as L cos alpha, L sin alpha 0. That you should be easy to derive. If you look at this figure, the projection point, because if this is L, and if you take this right angle triangle with the hypotenuse as L and this is the alpha, so you will get the coordinates of P prime as given here as L cos alpha, L sin alpha, and the z coordinates is 0. Okay. So, this much at least we can write, and as given in the figure, the direction of projection can also be written as dx dy minus 1, where dx dy are nothing but direction cosines given as L cos alpha, L sin alpha minus 1. This you should be able to derive yourself. I will repeat again, direction of projection is nothing but the vector joining the point P to the point P prime. So, you are looking at this vector here. So, you are basically looking at from 0 0 1 towards L cos alpha, L sin alpha 0. So, if you subtract one vector from the other, you will get the values as given here at the bottom of the screen as L cos alpha, L sin alpha minus 1. So, this is how the direction of projection is given, and the rest of the values can be obtained from the figure here. Okay. So, this was the figure which we were talking about. So, directional projection can be found out, or given directional projection also we can find L and alpha, the reverse. And of course, I leave it an exercise for you as a problem to solve what is the angle beta. What is the angle beta? Beta is the angle between the directional projection and the xy plane. Okay, directional projection and the xy plane. If the direction cosines of the DOP is given to you, I think that is enough for you to find out what is going to be the value of beta. So, this is another problem I am giving to you. I am not solving all the problems because I thought I should leave something for the student to work out, although there will be a list of problems, but still you should try to solve this problem out from the angle from the beta. Given the previous expressions here, all expressions given in this, if you have noted down, you should be and understood the figure, you should be able to calculate the angle beta. Okay. Now, just a few specifications left for to describe various specifications in terms of perspective and orthographic projection. That means, when you try to define a three-dimensional view, what are the parameters of that view you need to define. There are various types of parameters which are used for a generalized projection matrix, and given these parameters, given the object, the graphic software should be able to calculate and tell you, or you should be able to write programs which will give you the corresponding projection. Okay, I will go through the terminologies which are given here. The view plane VP, the first one which comes is the view plane, which is given in the big rectangular box, and the view reference point VRP is the center on which you have the 3 axes coming out. The VRP is a point on the view plane. VRP is a view reference point on the view plane VP. I have not written these corresponding terminologies, but I am, as I say, keep writing down yourself. VP is the view plane, VRP is the view reference point, VUP is the view up vector. Okay. VRP is the view reference point and VUP is the view up vector. I will define what is this view up vector. It is very important in 3D space to define what is up for you. Okay, what is up, which with respect to the up vector you can define your right, left and bottom, because in space basically you may lose your coordinates and you will not know what is top and what is behind and in front of you and things like that. So, you need a view up vector and a view, and the next terminology is VPN or view plane normal, which is this vector as given here. VPN is view plane normal. Okay. PRP is already you have seen, projection reference point. DOP also you know, directional projection, this we have seen. CW is center of the window, that is the center of this window in the view plane or the viewport. You can define a sub window of the view plane within which you will put all your in which you will all draw your figures, and the center of window is exactly the center of that small window, the grey color window within the view plane. Okay, that is the center of window CW, and VRC is nothing but the view reference coordinate system, which talks of u and v instead of xy in certain cases. Remember, the view plane normal is along the vector normal n, which is normal to the projection plane, or VPN, they are same, and the center of window, which is the center of the viewport, as it is called, the small rectangle running from coordinates u min v min to a maximum of u max v max in the uv coordinate space. Uv coordinate space is defined to define the view reference coordinate systems on the view plane. So, these are the terminologies. If you have missed anything, I repeat again: VP is view plane, VRP is view reference point, VUP is the view up vector, VPN is the view plane normal, PRP and DOP are known to you earlier, CW is the center of the window, and view reference coordinate, virtual reference coordinate system or view reference coordinate system is VRC. So, these specifications, once it is given, a complete three-dimensional projection geometry is defined, and now objects in 3D can be projected onto the view plane VP, or even the window which is defined between u min u max, u min, v min to u max v max. Okay. Well, if these are defined with respect to the COP or PRP, central projection or projection reference point, you can define a semi-infinite pyramid view volume for perspective projection. We said that rays come out from the object, intersect the projection plane and meet at the COP. You can visualize the other way around, where rays come out of the center of projection, okay, they come out, intersect the a projection plane and goes towards the object. Basically the rays, the light rays from the object have to come towards the projection plane, and these rays are not parallel anymore. When you talk of perspective projection, they are parallel in the case of oblique, orthographic or parallel projection, but in perspective projection these rays meet at a point called the COP or PRP. So from the previous figures we know what is a VP, which is the view plane, we know what is the view plane normal, we know what is center of window, we know what is the VRP or the view reference point, and we know the virtual coordinate system and the COP. So this type of structure defines a rectangular base pyramid, which is a semi-infinite, in the sense that you can try to visualize that these rays form an infinite pyramid in one direction, and all objects in that pyramid which is infinite in one direction only forms the view volume of your perspective projection. You can visualize a pyramid with a rectangular base, you can keep drawing away the view plane away from the COP, and the volume which you get is actually now called the pyramidal volume is semi-infinite, because infinite only in one direction. And this is how you define what is called as the pyramid view volume for perspective projection, and it is semi-infinite. Just to describe once again, although we say it is a semi-infinite, but to make matters easy for the graphic user or the graphics designer, we make the semi-infinite pyramid a finite pyramid view volume for perspective projection. How do you do that? Okay, with that semi-infinite pyramid, I define what is called a front clipping plane and a back clipping plane. Okay, we talk of clipping later on, but here you can visualize that the objects which are now all within the volume between FCP and BCP, that is front clipping plane and back clipping plane, which will intersect a pyramid and create a finite view volume for perspective projection, those objects will be visible. They should be between the FCP and the BCP. If it should be between the front clipping plane and back clipping plane, because nothing on the back side of the back clipping plane is visible, nothing on the front side is visible to you, and of course you can put your VRP and the VP, that is the view plane and the view reference point, in between, anywhere between you can actually keep it even in front or outside this range between FCP and the directional projection, as you see, is also marked. It is actually normal, but in the reverse direction of the view plane normal. This is the case of a finite pyramid view volume of perspective projection. And I go back to the previous slide. This was the case of a semi-infinite pyramidal view volume, and this is the case of a finite. So you can visualize yourself both are pyramidal structures. One is semi-infinite or almost infinite, and this is a finite view volume. This finiteness comes from the two planes, the front clipping plane and the back clipping plane respectively. Coming back to parallel projections, infinite parallelepiped view volume can be defined with respect to parallel projection. Now the rays which were converging out with respect to the COP or PRP in the case of perspective projection are parallel now. Okay, in the case of a parallel projection which could be orthographic or it could be oblique, typically let us only visualize orthographic type of projections here. The COP has vanished to infinity. Okay, you don't see a COP, there is no central projection because the rays do not meet, or you can say that the rays meet at infinity. Since the rays meet at infinity, the rays are all parallel. They are all parallel, and they are also normal to the plane. Okay, if you see the normal n, the view plane normal, which is also normal to the projective rays, orthographic projector rays which are parallel. This is also parallel to the direction of projection running from PRP to the center of the window. You can define the direction of projection here, where the direction of the projection is the direction through which the rays will be traveling. They run from the PRP to the center of the window or towards the view plane, and that defines the DOP. It is also parallel to view plane normal, but in the reverse direction. View plane normal is parallel to a direction n. which you can specify earlier, and the view and the VRP could be defined anywhere on the screen. It may not be only on the CW or the center of window, it could be the VRP is defined in this case in the bottom right of the screen. It is all, you are free to define these coordinates, but with of course certain constraints, and they should be all consistent with respect to each other. The VRP could be anywhere in the view plane, center of window is the center of the viewport, the grey color central window, and PRP, the line joining PRP the center of window is the direction of projection. So, that is the infinite parallelepiped view volume. Why infinite? Because if you see, I have drawn 4 such rays which are intersecting the projection plane normally, and they moved on both directions towards infinity, and you can visualize that I have got a rectangular parallelepiped of infinite size. Okay. So, the depth basically there is a height and or the length and a breadth, but along the z axis or along the direction of projection it is infinite. So, that is an infinite view volume, like an infinite pyramid which we had in the case of perspective. Now, this infinite pyramid becomes an infinite parallelepiped in the case of parallel projection. Just to define it more in a better form, well, that infinite parallelepiped can be made a finite parallelepiped. As in the case of perspective, we remember we had a semi-infinite pyramid, we made a finite pyramid out of that. So, similarly here also we can make a finite parallelepiped view volume, VV is also the term used for parallel projection, and like in the previous case we also can have a front clipping plane and a back clipping plane, the FCP and the BCP, okay, which sits in front of the VRP and on the back side of the VRP or the rather the view plane. Okay. So, you have the FCP or the front clipping plane on one side of the view plane, you have the back clipping plane on the other side of the view plane, and all objects within this finite view volume, that is the view volume defined by the front clipping plane, back clipping plane and the corresponding dimensions. If you visualize, all sitting within that box, all objects within, or all points, lines and objects and surfaces within that particular view volume will all be visible to the viewer on the view plane or the window or the viewport which you define, and all objects which are outside, all objects which are outside this view volume will not be visible. So, it is always good to define a finite view volume either in the case of parallel or perspective, so that you know what are the range or the dimensions, range of values along each x, y and z directions which are visible to you. Of course, if you take a digital camera or if you are seeing through your own eye, you know that only a finite range of the world is visible to you, and that too in front and a little bit to the side and top and down. You may not be able to see definitely what is on the back side of you, you may not be able to see objects which are too far from you on the front side, and also definitely on both sides if they are highly oblique to the left and right side, if they are on the two extremes you will not be able to see the object. So, you need always see, of course, in the digital camera and in our eye we have a perspective nature of viewing, but either perspective or parallel you always see a finite region in space or in the world whatever, and henceforth you always have a back clipping plane and a front clipping plane, and of course, the two dimensions on two sides you will not be able to definitely see what is back to you on the reverse. Okay. Okay. So, with respect to this point, I would like to wind up the discussions on three-dimensional transformations and move on to the next lecture, which will be basically an extension of three-dimensional transformations, but I have given it a different name, which will be going towards three-dimensional viewing and clipping. Although there is a separate chapter on clipping algorithms, but three-dimensional viewing geometry and all that, I thought to keep it separate out from three-dimensional transformations. We will discuss that in the next 1 or 2 classes as we go along. But before that, please, I have given here a list of problems and exercises which you should try to solve based on the last 2 to 3 hours of lecturing which we have done so far. And as we went along, of course, also I have been stating problems to you which you should work out. All these mathematics which is given to you, you should draw those diagrams yourself, you should try to derive those equations, expressions for the generalized transformations of all the matrices in terms of specifically rotation, reflection and perspective transformation matrices. You should derive all those expressions yourself, and then only you will get the confidence at least once or twice. And in addition to this, I must also mention here that I have given a few more problems which you can work out. I will just read out these problems. The first problem says, illustrate the vanishing points for the projection of a transparent cube in case of 3-point perspective projection. Remember, as we went through this lecture, we talked about 1-point, 2-point and 3-point perspective geometric or projection models, but I have only given figures for 1-point projection and 2-point projection systems. Okay. So, you will be able to visualize now what will be the scenario of the projection plane such that you obtain in the case of a cube a 3-point perspective projection. Visualize this and then try to draw and take a sheet of paper and try to draw projective rays, get the intersection points on the projection planes and then try to obtain the 3 vanishing points in the case of a cube for a 3-point projection. Okay. Question number 2 says, obtain the expression of the elements of the matrices which provide the generalized transformations in case of rotation about an arbitrary axis and reflection about an arbitrary plane. Now, I have given the expression in matrix multiplication form and I have given and worked out maybe two classes back the expressions of the elements of each of these matrices. Remember, we had a composite form which composed of translations, rotations and reflection also in question 2b, but I have not taken those two expressions and multiplied all those matrices and obtained a fundamental form. Please do that, it will give you a lot of confidence both in terms of matrix algebra and also in terms of matrix manipulations with the elements and also confidence with respect to this aspects of 3-dimensional transformations here in computer graphics. And so, take those expressions which are given there separately, take the composite form, substitute one by one, sequentially keep multiplying and obtain all the 9 or 16 elements, if it's a 3 by 3 or a 4 by 4. It could be, you could do this in 2D as well. Okay. You can do this in 2D, of course. In 2D, rotation is about a point and reflection is about a line. In the case of 3D, we remember the rotation is respect to an arbitrary axis, a generalized transformation I am talking about, and reflection will be respect to a plane. Okay. So, plane and an axis in 3D becomes a point and a line in 2D. You can, if you find the 3D transformation matrix too big, you can go back to 2D, take the generalized transformation matrices in 2D and try to get the expression of the matrix. I have given these separate forms, please multiply them. A special case of question 2 is question 3, where I am asking you to obtain the matrix which is a multiplication of that obtained in 2a and 2b. So, whatever answers you get in 2a and 2b, multiply them and get another matrix which what will this matrix give you? Yes, yeah, this matrix will actually give you a form of 2 successive operations of rotation and reflection. Generalized one. That means, if you want to rotate about an arbitrary axis and then reflect about an arbitrary plane, or even it could be vice versa, you can just reverse the transformations of 2a into 2b or 2b then 2a, whatever the case may be. The answer which you get in question 3 will give you the generalized transformation matrix which involves a composite matrix of 2 generalized transformations. What are those 2 generalized transformations in sequence? Rotation about an axis, reflection about a plane, or in 2D, rotation about a point, reflection about a line. So, that is question number 3. Question number 4 is a very interesting observation. Take the rotation matrix in 2D or 3D and prove that pure rotation about an arbitrary axis in 3D or a point in case of a 2D can be considered as a combination of another rotation and a translation. Okay, I leave this exercise for you to try out. That means, if you rotate by an amount theta, what you basically do is take another matrix where you rotate by an amount which is a fraction of theta or theta by 2, let us say. And to reach to the final point which you have rotated by theta, you need a translation, which you can do because you are talking of a point. Okay, we are talking with respect to a point. So, a combination of a rotation and a translation gives you another rotation about a point, or any arbitrary rotation can be expressed as a rotation and then a translation to the final destination point. So, please, you can prove that very easily. You can do it in 3D or 2D by taking the rotational matrices. Basically, what you have to do is find the expressions of that translational components required to take you to that final point which you would have reached by a pure rotation. The last question is, obtain the scale matrix along an arbitrary direction. Interesting here, because the scale matrix which you have thought of is a generalized scale matrix which will scale in all directions, or we have scale coefficients along x, y and z. Now, if I say scale along a vector 1, 1, 1, okay, or any arbitrary vector I give which gives you the direction cosines along a particular direction, and I will ask you to scale along that particular direction. That means, I am asking you to derive in the last question a generalized expression or a generalized transformation matrix for scaling, like we did for rotation, reflection perspective transformation. Now, do it for scaling because we have done got the scaling matrices for special cases along x, y or z or all together. So, given along a particular arbitrary direction, what should be a scale matrix? Please try to solve all these problems as given here and also the problems which I have talked of earlier. It will give you a lot of confidence both in terms of vector algebra, matrix algebra and transformation matrix in both 2D and 3D transformations. So, we stop here and move towards the next lecture, which will be on 3-dimensional transformation and viewing. Thank you very much.